Everyone, welcome to Toronto Data Workshop. Our guest this week is Alex Coppock, who is an associate professor at Yale University. He's remarkably, seems to have a remarkable work ethic because he's not only got one book out this year, but he's got two, which I've never heard of. So the first one is Persuasion in Parallel, How Information Changes Minds About Politics. So that's being published by University of Chicago Press. But the reason that he's our guest today is the second book that he's recently published, and that's called Research Design in the Social Sciences, Declaration, Diagnosis, and Redesign, and that's being published by Princeton University Press. The nice thing about this book is that I suspect the software came first and the book came second, and so the book explains how to use some software, which is especially useful if you're interested in research design in the social sciences. So thank you very much for joining us, Alex.
Rowan, thank you so much for inviting me, honestly, and thank you all for spending your noontime on Friday with me. I know that there's just like always a million things that you could be doing with your time, but you're spending it with me, and I really appreciate that. I want to tell you a little bit about how this project got started and give you a little bit of expectations of what to expect from today's talk. So Graham McCartan, and then at the time Jasper Cooper was also working with us. We all were at Columbia. Jasper and McCartan were going off and doing field work, and they needed to like simulate complicated data structures that they were encountering in the field, like some nested hierarchies and things like that. So they wrote some code to be able to do that more efficiently. Back in New York, Graham and I were we were designing experiments where we were doing simulations to understand power analysis. And as soon as you finish one simulation, then someone says, okay, but what if you change this? And so then you add a layer of a loop, and then you loop over a parameter. And then someone says, oh, that's fascinating. But what if you change like also vary something else? And so you add a third layer of a loop. But then when you do that, it turns out that actually you need like some other statistic that you hadn't been collecting. So you need to rejigger the whole thing. And so what happened was that like we would be writing these tangled nests of code with ever increasing layers of loopedness, and you couldn't like use the code from one project for the next, or you have to really adapt it hard. So we thought there's got to be a better way. And that's when we started writing DeclareDesign to do simulations. So the idea here is that we're going to use software to simulate our research designs before we do this. And I know that this idea is like in the air, especially in this crew, because step 2 of Rohan's book is you got to simulate. And so like this is going to be a zoom in on step 2 on simulating. The big insight comes from when we realized that in order to write general purpose simulation software, you need to know what it is that you need to simulate. So that's where we get research design theory coming out of software writing. So this is like exactly the opposite of how you're supposed to do it, where you come up with the theory first and then find the implementation. No, we were like messing around with the implementation, and we realized, okay, so what is the thing that we need to say about a research design in order that when you do the simulation, you get the right answer, or you get an answer that's interpretable. And we come up with the MIDA framework. That stands for model, inquiry, data strategy, answer strategy. So MIDA framework, MIDA. And it turns out that this framework is extremely flexible. So we have not encountered a research design that we can't state in terms of MIDA. So you might say, oh, well, that flexibility must mean that it's useless. And so there's a sense in which I'm just restating things that you already knew, putting it in those terms. I'll say that there are, to me, just such huge payoffs to putting things into those 4 categories, because sometimes you think that you're fighting about whether you should use logit or probit versus OLS, when actually what you're fighting about is what parameter you're estimating. So that's a question about the inquiry. So stating these things of like, what is it that you're trying to learn, i.e. what is your inquiry, can help you make choices about what choices you should make in your data strategy, what choices you should make in your answer strategy. Okay, so once we did that, we realized, oh no, our software implementation is totally crap. So the DeclareDesign version 1.0.0, which is the one that's on CRAN now, is probably the 5th version of DeclareDesign that we've written. We finally hit on ggplot for research designs. So a ggplot adds together plot elements. Then when you render it, it takes all those plot elements and then generates a plot. That's different from the base R graphics thing, which is like a pen and paper metaphor, where you're just constantly drawing on a canvas that you've set up. So ggplot adds graph plot components together and then yields a plot. DeclareDesign adds design components together and then yields a diagnosis. So that's going to be yields a design object from which you can get simulations, you can get simulated data, etc. I've given this talk like a bunch of different ways where I do like the theory first and then the application, or the application first and and it always works better when I do the application first and then the theory. And so that's what I'm going to do now. I'm going to screen share and I'm just going to do a basic 2-arm randomized experiment in DeclareDesign. We're experimenters, so that's the first thing that we reach for. I'll say that you can use this for any kind of research design, qualitative, quantitative, observational, experimental, descriptive questions, causal questions. So all of the 8 cells of those 3 pairs can be characterized in this way. That said, I'm going to do the design that I use in my daily life the most, which is a randomized experiment, and give an example of that. And then we'll move to exploring the MIDA framework once we have something in mind. Okay, so going to just go and screen share. Dangerously, I'm going to share my whole screen, but I think I've cleared it up. I'll turn off my email, how about? All right, so library, tidyverse, always. Library, DeclareDesign. So DeclareDesign is going to load randomizer, fabricator, and estimator. Randomizer does random assignments and random sampling using terms from the Gerber and Green 2012 textbook. So block random assignment, block and cluster random assignment, et cetera, et cetera. Fabricator, that's what McCartan and Jasper's work turned into for fabricating hierarchical data structures. And then estimator, that actually might be the package out of this that gets the most use, because what it does is it in R gives you robust standard errors for OLS easily, which was hard, and forever people were going to Stata of all things and paying outrageous amounts of money per year in order to do comma robust. So finally we wrote it in C++, so it's really fast. And then along the way, we saved the inverted matrix so that we could then use that for the standard error estimation. So estimator does flavors of robust standard errors for our linear estimators like OLS and IV. And I recommend it. Okay. So the first thing we're going to do is we're going to make a design object. And I'm going to declare my model. So MIDA, the first feature is a model. I'm going to say that I've got 500 units. I'm going to say that there's some unobserved variable about them. I'll pretend like it's normally distributed. And now I'm going to make potential outcomes. Potential outcomes. Y is distributed according to as.numeric. Is it the case that 0.2 times z plus u is greater than 0? That's going to be my whole model. So what do we get for that? So this is one draw from that model. I get 500 subjects and they've got a little ID variable. How useful. I've got that unobserved difference variable for each of the units. And then that potential outcomes function created 2 variables, yz0 and yz1. So my model of the world is that there's something that is idiosyncratically different about each of these units, and I'm not modeling what is idiosyncratically different about each of them. And then I'm saying that they each have 2 potential outcomes, a treated potential outcome and a control potential outcome. That's my model of the world. This model could be very wrong. There could be interference across units. There could be multiple potential outcomes. There could be compliance questions, right? But for right now, The model is simple, and it only includes 2 potential outcomes for each unit. To this, I'm going to add an inquiry, declare inquiry. And the inquiry I'm going to add is the average treatment effect, which is the average difference between YZ1 and YZ0. Now, when I do this, I say, let's just run the design one time. The only thing that has happened so far in the design is that it defined my inquiry. And right now, in this particular draw, the value of the inquiry, which we call the estimand. So why is it that we use the word inquiry, not the word estimand, which is so much more common? I almost kind of regret this choice because it creates this friction. When I say inquiry, I also mean estimand. However, there is a difference between a question and its answer. So the question is, what is the average treatment effect? That's the inquiry. The value is 0.64. That's what we're calling the estimand. So we just need 2 words, and those are the 2 words that we landed on. Being upset about the word inquiry is not a reason to not use this framework. Okay, so that's just to distinguish between these 2 things. We need words to distinguish them because otherwise it doesn't work. All right, in this particular draw, the value of the inquiry, the estimand, is 6.4 percentage points. In another draw, it would be different. So why is it different each time? It's because I'm imagining that I'm drawing these units from a superpopulation. You don't have to imagine that you're drawing them from a superpopulation. You could have a fixed set of units that you're imagining you're doing an experiment from. But when I dip my dipper into Mechanical Turk to obtain 500 research subjects, I'm imagining that they are a draw. And so you can build that kind of uncertainty in by having something like this. If you are imagining that it is really just among the 100 senators that are in the US Senate, then you could have a fixed population. So there's full opportunity for that kind of flexibility here. That's why the value of the estimand bounces. This is not estimation uncertainty. This is that the actual value of the estimand changes from draw to draw. Okay, that's the theoretical half of the design. I've got M and I've got I. Now let's move over to the empirical half of the design. How is it that I'm going to sample units? How is it that I'm going to randomly assign units? How is it that I'm going to measure units? Let's imagine there's no sampling step. I'm going to sample everybody. So I'm only going to have an assignment step, declare assignment, Z equals complete RA, Z, and I'm going to set the probability to equal to 0.5. What complete RA does is it assigns exactly half or exactly prob times n of units to treatment and the remainder to control. You can contrast that. Well, here, let me just show you what that looks like. So now I can do data, draw data, design. Error. Now when we look at the data set, we've added this variable z, and I promise that there is exactly 250 units with the value 1. If I had done simple RA, each time you do it, let's see, data, $z, table. In that particular draw, there's only 246. Okay, so complete RAs, that's what we'll use. Now we need to measure outcomes. We've randomly assigned, but we haven't actually revealed the post-treatment outcomes. So we'll do declare measurement, y equals reveal outcomes, y on z. And that reveal outcomes is a generalized switching equation. So it's smart and knows how to pick out the right potential outcomes column to generate the revealed outcome. If you had multiple treatments, for example, this makes your, instead of having to do like a complicated case when, this one just handles that for you. Now when we draw data, we have the z and the y columns. Notice that if you were to do an experiment, you would only get these last 2 columns. Those is what you would observe. These columns, YZ0 and YZ1 would be hidden from you. In simulation world, we can now see how close a difference in means estimate calculated on these guys would be to the true average treatment effect in that particular draw of the data. Let's do exactly that. I'm going to declare an estimator. I'm going to say I'm going to get y on z. The method that I'm going to use is equal to difference in means. My inquiry is equal to the ATE, and I'll just put a label on it that this is the difference in means. Now when I run the design, down here, I get, for this inquiry, I get the answer in that particular draw is 8 percentage points. I randomized Z and I took the difference in means. My estimate in this particular draw is only 1.6 percentage points with a standard error of 4.5 percentage points. So what we want to understand is what is the distribution of possible estimand pairs over many draws. So you could run design over and over. Each time you're going to get a different one. More efficiently, you could do simulations, gets simulate design of design. By default, it does 500 simulations. This is the part of the talk where I try to like keep you distracted while it's simulating. Oh, look, it's done. Here we have the simulations data frame. For each simulation, I have one draw of the estimand and one estimate. So something that you might want to know is what is the average estimand, mean estimand? What is the average estimate? Mean estimate equals mean estimate. Or what is the bias? That's going to be equal to the mean. I always have to like remember this one hard. It's estimate minus estimand, because if the estimate is bigger than the estimand, then it's positive. Okay. Oh, look. It's unbiased, right? Like we knew that.
Estimate twice.
Ah, that was really zero. Okay, it's pretty close to zero, right? So we knew that under random assignment and no problems with compliance and no problems with attrition, that a randomized experiment is going to give us an unbiased estimate. And we've recovered it here. So each of these things, we call it a diagnosand. That's another word that people don't like. And I totally respect that. It is a feature of a design that we are trying to diagnose. So we call it that which is to be diagnosed, a diagnosand. A more like a very common one is power, which is how frequently is it the case that the p dot value is less than 0.05? And that happens 43% of the time in this particular simulation. Okay, one thing that's frustrating is that these are simulation estimates of those diagnosands. And so you could be worried that, is it really biased? Does it have negative bias, or is it close enough to zero? So one thing that you can do is just pass the simulations data frame to diagnose design, simulations. What it does is it gets bootstrapped standard errors on those things, bootstrapping the simulations data frame itself. It has a series of default diagnosands that it'll do that for you. So this power is 43% plus or minus 2 percentage points. If you need better precision than that, it's all you need to do is just pump up the simulations in order to get a better. Now we have to wait just a little bit longer. We're doing it 1,000 times, during which time I'll answer Michael's question.
Yeah, so what is that last step doing? What's the advantage of doing that last step rather than just running a whole bunch of simulations once?
Sorry, this last step here, you mean?
Yeah.
So this is like a lumping and splitting programming problem that me and my co-authors, we went back and forth just over and over and over again. Diagnose design could take a design object, simulate the design, and then it returns two things. A simulations data frame, that's the thing that we already looked at. That's got 1,000 simulations. It also has a diagnosands DF. This thing tells you what is the average and then its estimate of the standard error of that estimate of the diagnosand. And so it gives you simulation uncertainty so that you know when to stop pumping up the sims. That's basically the reason, is that we would be doing these things over and over and over again and not knowing whether variation that we're seeing is simulation error or what. Well, it turns out that statistical theory has got an answer for you, and we can just get the simulation uncertainty directly like that. Okay, so indeed, when we increase the simulations to 1,000, the estimate of power, the standard error on that thing went down. Okay, that is one instance of implementing the MITA framework in DeclareDesign. Let me now should have gotten this open beforehand, excuse me. Okay. Now, normally I like to do this thing at the whiteboard so I can like be dynamic and keep your attention. But instead, I'm going to do a slow reveal on the figure. This is the figure that I wish we had been able to put on the cover of the book. When we said, couldn't we put it on the cover of the book? They're like, do you have any idea how to sell a book? No, you don't know what you're talking about. And so this is the idea that we want to communicate. So it actually appears 3 times. It's the frontispiece. So it's not really the cover, but it is the first thing you see when you open the book. It's figure 2.1 and it's figure 5.1. And that's because it's really important. So I'm going to walk you through it. In the middle row, we're going to start with M, capital M. Capital M is the set of theories you have about the world. It's a set of theories. And this is a complicated idea. But if you only had one theory of the world, you would not need to do any empirical study. You wouldn't be uncertain about anything, right? What we're saying is that your theory includes a range of possibilities for what the effect size is, a range of possibilities for how the outcome is distributed, a range of possibilities for how the outcome is correlated with the covariates. You don't know all those things, but you allow your mind to have many of these possibilities. The world is one way or another. Every unit has one value of each potential outcome. The correlation is one way and not another. And if you don't believe in M star, that is to say, you don't think that there is a truth about the world to go discover, then we should abandon empirical research, right? Like if you are so POMO that you can't believe in M star, then there is no point in doing an empirical study one way or another, except for perhaps to get a job at a university, right? Like to learn about the world, you have to believe that there's something to learn. That something to learn is going to be called M star. Okay, so now you have a question about the world that we're going to call the inquiry. The inquiry conspires with M star to create the true answer to your question, AM star. That is the true value of the estimand. That is what the actual target value is. Now, I'll say that there are some times when you don't ask your question correctly. You ask a question of the world that returns NA. Here is an example of that. Suppose that you have an intervention that saves the lives of newborn children. That's what you have come up with that intervention. Now you've got an outcome variable is what's the effect of that intervention on birth weight, or sorry, on the weight of the child after a year, right? For those children who don't survive in the control condition, but whose lives you saved in the treatment condition, that value is undefined. They don't have a weight in the control condition, they only have a weight in the treatment condition. And so then when you say, I want to learn the average treatment effect on weight for age at year 1, that value is undefined because it's NA for some of the units that it's defined over. The way that you would have to get around this is to redefine your inquiry to be, what is the effect on weight for age among those units that would survive in the control condition and would survive in the treatment condition? Of course, defining those units is very hard because it's a principal stratum. It's not something that you can just observe. It depends on whether or not you were assigned to treatment. So that just shows that some of the questions that we have, and this is common in the literature, is that like many of the outcomes are downstream consequences of other outcomes. And so it's not obvious that you can ask for the average treatment effect on each of them. You might need to ask something different. So this comes up in audit experiments all the time. What is the effect of the treatment on the tone of the email you get back from the recruiter? What emails that are never sent have no tone. So you can only estimate that value. AM is only defined among those units that if you emailed them in both conditions, they would write back. Okay. AM star. Let's keep going down the middle. Now we have a data strategy. A data strategy is a set of procedures. It's crazy. I just couldn't quite believe it when we wrote it down, but it's true that data strategies, anything that's in a data strategy can be described as a sampling procedure, an assignment procedure, or a measurement procedure. There's nothing else in them. And so like when you're thinking about qualitative research, you're thinking about case selection. That is an assignment, sorry, that is a selection procedure or a sampling procedure. When you're thinking about assignment, those qualitative researchers put their subjects in the condition of being interviewed and not in any other condition. And then when they take their measurements, the measurements are the result of that interview, right? So you can state the data strategy of a qualitative interview research design in terms of those three features of a data strategy. Data strategies are sampling, assignment, and measurement. Your data strategy conspires with the real world to create a data set D star. That data set D star is the thing that ends up on your computer. That's the thing that transparency advocates are telling you to put on the internet. D star is the data. It is separate from capital D, which is the procedures that create the data. And so like one of the frustrating things is when people talk about doing data science, they kind of take D star as given, but D star is created by the confluence of researcher choices in D and the world in M star creates D star together. A similar, now we're going to take the answer strategy, which is the set of procedures that you apply to the realized data set to generate a D star. A D star is your estimate, your p-value, your inferences. It's really what goes in the results section of a paper. All right, so a lot of times people are just telling you a D star, and they kind of omit everything else about the design. And then they say, oh, I know the answer. I know it's a D star. And you're like, why do you know? The answer to why do you know that a D star is the answer depends on all of the other components in the figure, okay? What do we really want to know is why is a D star a good guess of AM star? And the truth is we can't know that just by learning a D star. In fact, we can't know that even if we had D star. So like the transparency revolution is great and everything, but I still don't know if the answer is right, even if I have the data set, right? What I need to understand is the properties of the design over a range of models in M. So the top row is reality, the middle row is design. Now we're going to get down to simulation world. Each of those theories you entertain in capital M can be represented as a draw lowercase m. Like when we looked at the data frame here, lowercase m is u, yz0, and yz1. That's one draw from m. If you wanted to iterate over a range of possible values for the treatment effect, each one of those things would generate a different lowercase m. Just like above, M and I are going to conspire to create AM. D and M are going to conspire to create little d. That's little d is Z and Y. And similarly, you're going to get a simulated estimate, AD star. Now you really can compare AM and AD so that you can say, at least under this model, I have a pretty good estimate of the difference between AM, or I can directly estimate or calculate the difference between AM and AD. And then over many possible draws of M or many possible realizations of capital D, I can characterize the distribution of estimates AD relative to AM. Okay. Here's the final figure that shows up in the book. And it's like a lot to see all at once, which is why I wanted to reveal it slowly. Let me just recapitulate a couple of the things that I said along the way. First is that designs have a theoretical side, M and I, and an empirical side, D and A. And we make that distinction because these are things that you do in the world. This is what we criticize. Oh, I don't like your assignment procedure. Oh, you're using the wrong estimator, right? We talk about these sorts of things. And a lot of times, discourse in review memos or in seminars are maybe about, did you control for something? Did you use fixed effects, et cetera, et cetera? Many times, when people are talking about those things, they are subtly changing things on the theoretical side. A good example of this is in an observational study. When you control for X, you actually re-weight the data such that you're upweighting those units that have high variation on, upweighting those classes of units that have high variation on the treatment variable and downweighting the others. So you thought you were shooting at the average treatment effect for all countries in the world, but it turns out that it's only those ones that net of covariates still have variation that you end up studying. So this is the point made by Arnaud and Samy in their criticism of selection on observables approaches for studying the average treatment effect. So like, that's just to make the point that you want to keep separate critiques about estimation procedures while holding the question that you're trying to answer constant, and it can interact in subtle ways. Okay, the top is the reality. That's what happens when you actually do your study in the world, and the bottom is the simulations world. You can learn about what happens in the simulations world, and you can't learn about what happens in reality. So the gambit of doing empirical research design is that the one that you imagine, or the set of worlds that you imagine, bracket the real world sufficiently that we actually make progress. So that's the gambit. I want to go back to our simulation and show you how we could change the research design in a couple of ways in order to improve upon the diagnosans that we calculated for the simple difference in means estimate. One is going to be a change to the data strategy. Imagine that we block on a prognostic covariate. How does that change the sampling distribution? Or alternatively, leave the data strategy alone and change something about the added answer strategy. Let's control for that binary covariate that we would have blocked on. Right? So that's going to be the exercise that we do now. It's stressing you out that this is unsaved. I get you. This is... Okay. Let's call this original design. And I'm going to add to it a binary covariate, which is downstream consequence of that unobserved variable u. So imagine that this is a proxy variable for u. We'll have it be r binom n equals n. We're going to flip one coin for each unit, and we're going to have the probability be p norm of u. Right. So I don't directly make x correlated with potential outcomes, but I'm making it correlated with the thing that is determining those things. Now, when we look at the data, we'll see that we get that x variable. If you wanted to be very pedantic, you could say that in the declare measurement step, we measure that covariate, x equals x. Okay. So now we have that x variable that we can either block on or not. Let's do a blocked design. So the only thing I'm going to change here is that instead of complete RA, I'm going to do block RA. Blocks equals X. I'm also going to tell the difference in means estimator what the blocks are. Now, my inquiry is still the average treatment effect. My label, I'm going to say that, let's call this the blocked difference in means now. So nothing else about this design changed, except I measured a binary covariate, which I then blocked on pre-treatment. Let's compare, let's call this design blocked. Let's compare that to design adjusted. So now I'm going to go back to complete RA. I'm going to grab that from up here. Sorry. But instead of doing difference in means, I'm going to do y on z plus x method lm robust. My inquiry stays the average treatment effect. So even though I've now controlled for something, the target stays the same as the average treatment effect, and we'll call this OLS. Now let's make a list of designs. List, design, design blocked, design adjusted. If I do simulate designs, simulate designs is available to you if you're like, I'm not simulating one design, I'm simulating plural designs, and it's just an alias, so it's the same. Great. Oops, I meant to do just one. Sims equals 1. Okay. Now, why is that giving me a problem? It's giving me a problem because blocks equals X is not an argument to LM robust. Great. We get this nice error. You should simulate more than once. Okay, fine. We get that we've got these three estimators. They give different estimates. Let's now simulate this 500 times. And while we're waiting for that, I'm just going to set up the diagnosis. By group, by design. I think it's design. It's called design. Yep. Okay. Design 1, that's the one that was unadjusted. Let's get the standard error in there. SD estimate equals SD estimate. This isn't as powerful as I'd hoped it to be. But nevertheless, that's how much you have increased your power from blocking or covariate adjustment. Let's see about the standard errors on that by doing diagnose, design, simulations. Right, so I've got a standard error of 2 percentage points. Adjustment helps, blocking helps. They help by about the same amount. I'm sorry that this is not exactly showing that to be true, but it is true. So that's how you can switch things about A or switch things about D in order to understand their properties. Let me pause there for a second and ask if there are comments or questions. That's no problem. I'd like to, I've got about 15 minutes left, or that's how long the session is. I want to spend it on 2 more things. One is I'd like to make a couple of comments about how this relates to like broader issues in empirical work. And then I'm going to give you a brief tour of chapter 3. Actually, I'll go ahead and just do that first. I have Rowan's book up here because I think it's really important to say this is about step 2, right? Simulate and consider those simulated data. This changes what you do. By simulating, you change what you do. And if obviously that's why that step is there. If it didn't change what you do, then it would just be like, I don't know, Rowan says you have to do busy work. No, this like literally changes the procedures that you end up following because you weigh different choices. When you're doing observational work, sometimes the actual data differ from what you simulated. And so like that can be a source of confusion and stress and tension that maybe will make you consider the resulting data differently. In prospective research, the simulation is about changing your data strategy such that the data set that ends up on your computer is the one that you want. What we just did is we walked through pretty much portions of chapter 2, which is how to do M, I, D, and A, and then redesign over features of D and A, and in order to learn about features of the design. So this chapter explains, or this part of the book, like walks through what are the choices in each of those areas that you might want to consider in general. The research design library splits up empirical research designs in the social sciences according to a split of I and a split of D. So we have descriptive inquiries that are about the world as it is, and causal inquiries, which are about the world under interventions, like the difference between what would happen if we did this versus that. Observational studies and experimental studies are sometimes like, there's like a conflation of observational descriptive, experimental causal. I mean, it happens quite often when like, I'll raise my hand and be like, oh, I noticed that you are drawing a causal inference from observational data. And then their speaker will say, oh, no, it's only descriptive. I'm like, excuse me, I know you're doing causal inference. Obviously you're doing causal inference. Defend your causal inference on the basis of your observational data, observational research design. You can't just pretend as though the inquiry became descriptive because you don't accord it as much weight as you would if it were from an experiment. Okay, that's to say that there are experimental studies that shoot at descriptive questions. That's like a list experiment. A list experiment is trying to get at a prevalence rate using an experimental method. An audit experiment is trying to learn about a rate of discrimination. It's an experiment, but it's shooting at a descriptive quantity. A conjoint experiment is trying to learn about how a person would choose between two candidates. We use experimental methods in order to learn about their choice among a huge range of possible candidates, but it's nevertheless a descriptive question, right? So then experiments can also be used to tackle causal questions. That's the example we've been working on. You can use observational studies to do causal inference, I promise. If that weren't possible, oh man. No, it's definitely possible to draw causal inferences from observational studies. For example, RDDs, process tracing in qualitative research is another approach to doing causal inference from observational data. And then we're very used to using observational studies for descriptive quantities, like do a survey, or maybe you do a case study and you're drawing a descriptive inference about that case. Okay, we divide up all of the possibilities here in like, here are all the ways to do observational descriptive studies with DeclareDesign starter code in each of those cases. What are some common inquiries? What are some common answer strategies, etc.? Like for observational causal, if you wanted to like set up an IV study, you've got potential outcomes that are about whether or not you would take treatment if assigned, and how your outcome variable responds depending on your compliance status and whether you were assigned to treatment. This regression discontinuity design helps you like think about generating data that are like a regression discontinuity design. So I'll say that the observational causal chapter is, I see it getting less use because people say, I have the data I have. Why should I think about the data I could have had or alternative data? And really, it's to understand what are the crucial assumptions that you're making about the data. And if they were at all wrong, how wrong would you be? Right. And I feel as though many observationalists are unaware of how consequential a selection of observables assumption is, or how consequential is a no sorting at the cutoff assumptions is. And so, like, yes, you could read those methods papers, or you could just simulate what happens if you're a little bit wrong. And that is a really important step here. Okay. Let me finish up by relating this figure to some important trends in empirical work. I alluded to some of these already. The credibility revolution. It's really about, is it really the case that AM star and AD star are close? Right? That's what everyone who's like caring about identification is really caring about, is it the case that our answers are getting close to the true values of the estimand? Sometimes what that credibility revolution has done is has changed which questions we ask. So the famous debate between Deaton and Cartwright and the IV folks is about whether or not the local average treatment effect or the average treatment effect is a reasonable quantity to be shooting at. And so it seemed like it was a fight about whether you should use OLS or IV, which is an answer strategy kind of question. But actually, what it's really a fight about is whether or not the local average treatment effect is economically important. And it used to be that people, by assumption, because they believed their models so much, that the average treatment effect and the local average treatment effect were one and the same. And so you were using an IV to get an answer to the question, what's the average treatment effect? But if you were to say, wait a minute, there might be heterogeneity in the causal effect of whatever it is you're studying, then the local average treatment effect and the average treatment effect might be different. So none of that has anything to do with statistics. That's fully an inquiry question. That's a theory question. So this helps us to think about which side of that is at issue in the debate. Is it M&I or is it DNA? Another big debate is the open science practices. So open science practices, like at many journals now, you have to give your code and your data. What does that mean? You have to give D star and you have to give A. The paper is supposed to be a record of AD star, right? So in the end, you're like asked to give these three things. That's great. I would really like it if people gave me those three things. I would really like it if they gave me all 12 of these things. Well, you definitely can't give me these two. So 10 of these 12 is what I would like to learn about. I'd like to learn about, what is your theory of the world? What is the question that you're answering? And why is it you think that your design is good for it? Right? So that would be what I would count as transparency. What about a pre-analysis plan? Pre-analysis plans are like supposed to constrain people about what A's they apply to their D stars. That's like you have to like say in advance what your A is going to be. Okay, what I really care about though is whether your A is appropriate for your D. Like it happens constantly that people are pre-registering that they're going to do analyses that are totally inappropriate, right? And so just that the fact that you pre-registered your mediation analysis doesn't mean that you get to publish it, right? Like there's nothing in the data strategy that justifies your mediation analysis, for example. So that's to say, in your pre-analysis plan, what do I really want to see? I want to see MIDA. I want to see an example of you applying A to simulated data. That's the easiest way for you to communicate to me what it is you're actually going to do, right? So that's a way in which we can learn about, think about pre-analysis plans this way. Michael, yes, please.
Yeah, I just wonder if you could talk a bit about so you get the simulations give you a lot of measures of uncertainty, but I wonder if you could talk a bit about how you build in not just one unobserved variable, but lots of variation in functional form or in just the sort of the distance from M to M star is huge. I mean, M is always wrong, right? And so, totally. and so the question is, how do you build in a set of variation on the model that you think makes you confident you've captured M star within the realm of your simulations?
Thank you for putting it in exactly those terms. Like that's exactly the question. It is the hardest part. That's why this chapter 6, is like an enormous slog, right? Because it's just so many different ways that you could be building your model and how you might do it in DeclareDesign. But like, that is to say, you want to be going over a range of possibilities. This text on agnosticism is some of our ways of trying to talk about that. Let me show you one example of redesigning under model uncertainty, right? So this is sort of the question is like, suppose that you're uncertain about your model, how do you go over a range of it? So one thing that you could be uncertain about, for example, is the effect size, right? So here, what we're doing is that each time I'm generating an effect size that is a draw from the uniform distribution between 0 and 0.5, and then I am doing my study on that random draw. This is a nice little trick because I don't have to iterate between each one of those things. I can simulate from it and then just use I can summarize this simulations data frame using low S to learn about these curves. This trick really saves you a lot of effort because you don't actually need to simulate over the whole space with 1,000 simulations. You can simulate sort of more sparsely and then simulate over this because you know that there's continuity across those things. So here's a situation where someone says, oh, the power of my study is 0.67. And you're like, what could you possibly mean about the power of your study being 0.67? Do you know already what the effect size is? That's crazy. I thought that you were trying to study it, right? So an MDE is a summary of each of these curves. It's the MDE is the spot where these curves cross the 0.8 threshold.
Right.
MDE is a fine statistic. It's a weird summary across this kind of uncertainty. I would prefer to see plots like this, where given the rest of the features of your strategy, call it something you don't know about the world, the true effect size. How does the design change? Let me give you another example. Experimental causal clusters. Probably the most consequential thing in a cluster randomized experiment is how much do outcomes vary within a cluster versus across a cluster. Let's call that the ICC. These 3 sampling distributions are from the exact same design with these 3 values of the ICC. So it's visualized here so you can see over on the right, ICC units are quite tightly clustered in terms of their outcomes and treatment effects. Here you can see that the clusters, there's overlap across clusters and what the variation is like. The sampling distribution is wide here because when you treat one cluster, it's like you only have one data point, right?
Yeah.
Which is just an example of something that if you wanted to design a study that's a cluster randomized trial, God bless. Please, you have to go learn about the ICC before you do that trial, because the power of it can vary enormously on the basis of that number. So those are 2 examples.
Yeah.
Still, but like your point stands, even if I can sort of do it, like what if you don't anticipate the appropriate, or even if you do anticipate, but you were still optimistic? One other thing that you could do, in part 4 of the book, we talk about the research design life cycle. So here we are planning. I'll think that you end planning by doing a pre-analysis plan, But before you do your pre-analysis plan, you do a pilot study. Here is a simulation of what happens if you first do a pilot study, then update your beliefs about how big you should make the sample on the basis of what you learned from the pilot. And you can see that you can still get it wrong. That's what you're supposed to do. Here's what you would have done based on your priors about the world, but you used a pilot to learn about it. And so you still make a study that's too small because a pilot's just one draw. But you need to get information from the world some way or other. So path studies and pilot studies is going to be one of the answers to the question in general. All right, that brings us up to 1 o'clock. The last couple things I wanted to say were, if you wanted to talk about meta-analysis, good Lord. What we have done for meta-analyses is if you are on the same topic, like if you have the same JEL code or something, then I'm going to go get one number from your paper and then average it together as though I am averaging together the answers to the same question across studies. This is just so goofy. And that's why people like Judeo-Pearl is like saying, this is like averaging apples and bananas to get the properties of oranges, right? Like that criticism totally holds unless you're willing to coordinate your meta-analysis on having the same I and having Ds and As that shoot at it. Okay, and so I'll leave it there. Thanks very much for letting me ramble for a full hour.